So we just examined the basic concepts relation. Now we came to this function side. Now we will be giving the third relation example, which is function. The other ones were equivalence relation, order relation, and the function relation. So we're going to explain the properties of this relation for the functions, and then we are going to define how we can find a function between the sets, of which elements are finite number of elements. So those two is going to be in this video then. Now, so we're going to escape from here, move it down, take this up, this one, and this one, open board, okay, take it out. Let me clear this area. Oh, you see here, what is it? There are two properties of the function relation. The first one is this completely specified relation. Let me read it first and then explain. If the relation R includes all the elements in the domain of A, then it is called completely specified relation. If you remember that there were two sets A and B, and we were going to have a relation here which includes the pairs A and B, like that. So we are saying all these set A elements must be seen in that subset if we are going to define the function. So if that property is included, that means all the elements of A are seen in this subset or in this relation. That's the first property. It is called completely specified. So that means all A elements are specified. The second property is functional relation. In a R relation, for each element in A, if there exists one and only one element corresponding in B, then it is called as functional relation. What we are saying is this, maybe in here. So that's my A1, A2, B1, B2, B3. So it says for an A1 here, there's going to be one element corresponding to this, which is not allowed. What this functional relation tells us, the same element do not have another pair which includes another element in here. So that means in A, there should be one element corresponding in B. So for this one, for example, for the same A1, there are two elements corresponding to A1. It should be one, it says. So this is not allowed if this one in. If this one in, this is not allowed. So this is called a property, functional property. If those two properties included in a relation, then that relation is called function. Okay. If I give an example that will make it easier, maybe. Let's say you got a restaurant and there is a price list. Let's say ice cream, it says 5 TL, Turkish lira that is, and something else, milk is 10 TL. So if you make a list, so here corresponds, so these are the what is available, and these are the prices. In that. So what it says here, if you say the ice cream is 5 lira, then you cannot say anymore ice cream is 10 lira. So this is not allowed. So one item, one price. But the opposite could be true, isn't it? You might say that, okay, milk, what else? Water, let's say. If you say ice cream is 5 lira and water is also 5 lira, no problem. So these are two different elements of A, might be the same B on the right hand side. So this is allowed. Let's say this A2 goes to B2. These two together is allowed because two different items correspond to just one item here. That means ice cream, water has got the same price. But ice cream should not have two different prices. So this is not allowed. So this is the origin of the fighting, isn't it? So restaurant owner is going to tell you, pay me 10 lira. You're going to say that according to that table, I would like to pay that 5 lira. You want to give 5 lira. The owner wants to take 10 lira. So how are you going to solve that problem? This is not allowed. That's why it is not function. If it is justice, then it is function. Okay. And there is a special case here. That's the definition of the function between two sets. And a relation, subset of a relation, is a subset of Cartesian product of two sets. Is the relation subset of this relation? If it has got those two properties, then it is called function. So that is going to be the range. That's going to be domain, isn't it? These are the other terminologies that we use. That is the domain of the function f. That is the range of the function f. Is also called. So another thing that we're going to introduce and use it in Boolean algebra is the functions defined on the same set. We are saying we are defining a function between these two sets, but these two sets are special sets. Why they are special, I'll explain to you. So we are defining the function two different sets here. We are saying let's do it for the same set from A to A. That's not the end of it. We are also saying that I am going to find a set. Instead of this A, I am going to have a new set. This set is the Cartesian product of A on it n times. So you are multiplying this set A, Cartesian multiplication, n times. So if you remember, if it is Cartesian product like that, it's going to have elements in it, A1, A2 time. So pairs. If these are just two, that means A square. If it is A to the power n, so inside that Cartesian product, you're going to get n tuples, A1, A2, point, AN. And then A1, A1, point, AN. So many n tuples like that. So if the domain is AN, A to the power n, Cartesian product of A n times on it, and the range is set A, then a function defined between those two sets is called n-array operation. Another name for it is n-variable function. We will be using this type of functions in Boolean function. That's why Boolean algebra. So that's why it is important. Um, we can give some examples. So another main thing that we face here is the number of elements of A has got finite number of elements. So in normal arithmetic, the number of if you are talking about the real numbers, this real number set has got infinite number of elements in it. But in this Boolean algebra, the sets that we are dealing with has got finite number of elements in it. So when it is infinite number of elements included for the sets, then the number of functions are going to be infinite. But for those, if you define the functions on finite set elements, then there's going to be a certain number of functions that you can define between those two. The next slide is related for this, how many number of functions that you can define. So let me clear this here first. So on the left hand side, there is an example. Right hand side is the generalization of n. So let's say, so different sets we've got here now. Different sets, I mean not A to A to B. So the number of elements, this is called cardinality. Cardinality of A is the number of elements included in this set. Cardinality of B is, we show it n, is equal to 2. So how many functions that you can define between A and B? So I'll make it a bit clear to you. A has got A1, A2, A3. So that is set A. So B, how are you going to write? How are you going to write set B? Now in B we've got two elements, B1 and B2. That means two symbols that you've got here. Any ternary permutations of these two elements represent one function. Example, B1, B1, B1 is one of the permutation that you can get from that. B1, B2. Triple permutation of it is going to be B1, 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 B2, or B1, B2, B1. It goes like that. Okay, so the number of permutations, if you've got two symbols, if you are going to make ternary permutations, so it's going to be 2 to the power 3. So there are 8 of them. So each permutation represents one function. So the number of functions that you're going to be is going to be 8. So this one is here is another example between the A2 to B. So when it is A2, the number of elements in A2 is going to be, you've got two, so you've got 3 elements in A. So the symbols are 1, 2, 3, so 3. So with these symbols, because of that A square, you're going to have 3 to the power 2 number of permutations. So these are the permutations that you're going to get written here. So maybe if I show it here. So these are 9 permutations written here. So you've got, in B you've got 2 elements, B1 and B2. So in this case, the number of permutations is going to be, since you've got 2 elements, you're going to use these 2 elements. 2 to the power 9 is the number of functions, because number of permutations of 9 elements is going to be 2 to the power 9. So this total number of is going to be that 2 to the power 9. If we generalize this rule, if you say the number of elements in B is capital N, then a to the n to n number of function is going to be this. N is the number of variables. These are the total number of functions that you can define between those two sets. It's given like that. So in this case, all these sets defined on the same set A. Okay, so these are the finite number of functions that we're going to have. That is the end of this one.